Interstellar objects like 3I/Atlas are reshaping the way scientists think about how planets form across the galaxy, offering a fascinating new angle on a long-standing scientific problem. These unusual deep space wanderers, unbound to any star and drifting freely through the Milky Way, carry with them the chemical fingerprints and structural clues of the distant systems in which they were born. When one of these objects passes through our solar system, as 3I/Atlas is doing now, astronomers view it as a rare scientific opportunity because such visits are exceedingly uncommon. In fact, in all of human history, scientists have only managed to observe 3 interstellar objects: 1I/Oumuamua, discovered in 2017, 2I/Borisov, observed in 2019, and 3I/Atlas, detected more recently. Each one has challenged our assumptions about how small bodies behave in interstellar space, how they are ejected from their home systems, and what secrets they might hold about the chaotic environments in which stars and planets form. Unlike comets that originate inside our solar system and travel along closed, elliptical orbits around the Sun, 3I/Atlas follows a hyperbolic trajectory, meaning it is simply passing through and will not return. It came from somewhere far beyond our heliosphere and will soon exit again into the galaxy, never to be seen by us again. Because of this fleeting nature, scientists rush to gather every bit of data possible: the composition of its dust and gases, the structure of its tail, the behavior of its nucleus, and how it interacts with sunlight and gravitational fields. Each of these details provides clues about conditions in the distant stellar environment where it originally formed. These interstellar comets are ancient messengers, carrying material that has remained largely unaltered since their birth, long before our Sun even existed. One of the most intriguing ideas emerging from recent research is that such objects could actually help trigger the formation of planets around other stars, particularly massive or young stars that possess swirling disks of gas and dust. These disks, called protoplanetary disks, are the leftover material from the formation of the star itself. Over millions of years, the particles in these disks collide, merge, and gradually build up into larger bodies. Eventually, through a process called accretion, some of these bodies become planets. This general outline is well established and supported by both observation and theory, and it explains how the planets of our solar system, including Earth, came to be. But despite its success, the accretion model faces a major challenge. Scientists struggle to explain how objects grow beyond roughly 1 meter in size. At this scale, simulations show that collisions are often destructive rather than constructive. Instead of sticking together and forming larger bodies, meter-sized rocks tend to smash apart or bounce away due to turbulence, high-speed collisions, and complex interactions with gas in the disk. This creates what astronomers call the meter-size barrier, a theoretical hurdle that seems to prevent particles from naturally growing into the kilometer-scale planetesimals needed to eventually form planets. Without a mechanism to cross this barrier, the standard model of planet formation remains incomplete. This is where interstellar objects like 3I/Atlas present a fascinating solution. A recent study suggests that if such an object passes close enough to a young star, the star's gravity could capture it, pulling it into its protoplanetary disk. Once inside, the interstellar object would act like a large seed, already far beyond the problematic meter-size threshold. Instead of needing to slowly grow from dust and small pebbles, this captured body would instantly provide a stable core around which gas and dust could accumulate. Over time, this process could give rise to a giant planet. The idea is somewhat similar to planting a fully grown tree seedling rather than waiting for a seed to sprout in poor soil. In a turbulent protoplanetary disk, where growth conditions are difficult, a ready-made solid object could bypass the early destructive stages of planet formation entirely. This theory not only addresses the meter-size barrier problem, but also suggests that giant planets might form more easily around stars that are likely to capture many interstellar objects, such as very massive stars or stars in dense regions of space where stellar clusters are tightly packed. In such environments, gravitational encounters between stars are more common, increasing the likelihood that wandering objects like 3I/Atlas could be drawn inward and incorporated into a new planetary system. If this is true, then interstellar objects are not just random visitors. They might be essential contributors to the architecture of planetary systems throughout the galaxy. Scientists are particularly excited about this possibility because it expands our understanding of the diversity of planets we observe. We already know that giant planets are surprisingly common in the galaxy, and some form at distances from their stars that current models struggle to explain. If interstellar objects are occasionally captured and used as the foundations of these planets, it could account for some of these puzzling observations. For example, planets that appear unusually massive or that exist far from the regions where accretion is thought to be efficient may have originated from these interstellar seeds. The discovery of thousands of exoplanets has revealed just how varied planetary systems can be. From hot Jupiters skimming close to their stars to super-Earths and mini-Neptunes in configurations unlike anything in our solar system. Incorporating interstellar objects into planet formation theories may help explain this incredible diversity. Moreover, the composition of objects like 3I/Atlas can tell scientists what kinds of materials might be spreading throughout the galaxy and seeding new solar systems. If such an object contains water ice, organic compounds, or unusual minerals, it could enrich a young star's disk with ingredients that influence the types of planets that form. This idea echoes theories about how life-essential molecules may be spread across the galaxy by comets and meteorites. Interstellar objects could play a similar role on a much larger scale, not just delivering life-forming ingredients to planets, but helping shape the planets themselves. The fact that we have observed only 3 interstellar objects so far underscores how difficult they are to detect. They move incredibly fast. Oumuamua, for example, sped through the solar system at about 87 kilometers per second. And because they are small and dark, they are often noticed only after they are already close to Earth. But as detection technology improves, especially with the upcoming Vera C. Rubin Observatory and its wide-field survey capabilities, astronomers expect to spot many more. Each new discovery provides further opportunities to study the physics, chemistry, and behavior of these alien bodies. The more interstellar objects we detect, the better we can understand how common they are and how significant their role might be in shaping planetary systems. The story of planet formation has always been one of enormous timescales, cosmic collisions, and delicate balances between physical forces. For decades, the scientific community has worked to reconcile the elegant simplicity of the accretion model with the messy, violent reality of protoplanetary disks. The introduction of interstellar objects into this narrative adds a new twist. Perhaps planets do not form exclusively from materials born within their own systems. Perhaps some of the planets orbiting stars across the galaxy, and even planets in our own solar system, owe their existence to ancient cosmic travelers that drifted in from elsewhere. If objects like 3I/Atlas can indeed jumpstart planet formation, then the Milky Way is more interconnected than we ever imagined, with stars and planets sharing building blocks across vast interstellar distances. As 3I/Atlas continues its journey through the solar system, scientists gather as much data as possible before it disappears into the dark once again. Although it will soon be gone forever, the clues it offers about the origins of planetary systems may leave a lasting impact on astronomy. Whether or not interstellar objects turn out to be the missing link in our understanding of planet formation, they have already sparked new curiosity and opened the door to theories that challenge and enrich our view of the universe. Planet formation is not a closed case. It is a dynamic field where every new discovery has the potential to rewrite what we thought we knew. And with each interstellar visitor, we get a little closer to understanding how the galaxy builds worlds, including our own.